I think we can start the live interaction session now. Uh, I think the participants have not joined today, so I think you can watch the recording later on once it is uploaded on on YouTube. Right. I will turn off my camera now. So, so, good evening and welcome to the week 2 of the live interaction session. Uh, this course is brought to you by NPTEL. The name of the course is Advanced Reinforced Concrete Design, and the course instructor is Professor Surya Prakash from IIT Hyderabad. And this live interaction session is presented by me. My name is S. Lalit Sagar. I'm a doctoral candidate and PMR fellow in the Department of Civil Engineering at IIT Delhi. And this will be the agenda for today's session. So, in week 2 of this course, right, yeah. So in week 2 of this course, we uh, covered the second module. Okay, excuse me. There was a okay. I think we can continue from here. So in week 2 of this particular course, we considered this module 2, which is based on the materials that is used in the reinforced concrete construction. So module 2.1 consisted of the discussions on the cement and moreover the short-term properties of concrete. And module 2.2 consisted of the properties of concrete in the long term. And in the module 3, we considered the properties of reinforcing steel. So I'm just going to briefly explain uh, what were the contents of each of these modules. So in module 2.1, we considered the types of cement and their basic hydration process, and we considered the stress strain behavior of concrete under compression and tension. Then we considered the behavior of concrete under multi-axial stresses. Then we discussed about the high strength concrete and then the lightweight concrete. That is to say, what are the constituents of the high strength concrete? What are the constituents of lightweight concrete? For example, by reducing the specific gravity or the density of the coarse aggregates, we can effectively reduce the uh, density of concrete. And what are the properties which are required in order to qualify as a lightweight concrete? So we discussed certain uh, aspects like these in the module 2.1, where we were concerned with the short-term properties of concrete. And then we also considered the various failure theories of concrete under a combined stress state. Okay. So in module 2.2, we looked into the long-term properties of concrete. That is, while in module 2.1, we considered how the concrete behaves uh, in the short term. So we studied how the properties of concrete vary with the age, that is, there are certain behavioral aspects such as creep, shrinkage, and the temperature effects on the material structural behavior, which were discussed in module 2.2, right? And in module 2.3, we considered the properties of reinforcing steel. That is, what are the different grades of steel that are available, and then what is the stress strain behavior of steel rebars, uh, that is, when they are subjected to tension, how they are going to behave, and what will be the stress strain properties. And then we considered the tension stiffening behavior of concrete. Okay, so these were essentially the contents of week 2, and now we are going to get into uh, the discussion, that is, the we are going to discuss some of the sample questions from this module 2 on the materials, which is going to help you in solving the assignment problems, and then develop a more comprehensive conceptual understanding of the concepts which were discussed in the week 2 of this particular course. Okay, so with that introduction, I think we can start with the question 1. So the question 1 pertains to the Box compounds, that is, the products of hydration, right? So the first question is, I correctly arrange the Box compounds in cement. Uh, so good evening. We have already started the session, so we can. Uh, the question 1 is already there, so you can try to attempt. Okay, so the first question is pertaining to the Box compounds. That is, we need to arrange the Box compounds in terms of the rate of strength gain in an ascending order. Okay, please take 2 minutes and let me know what is the right answer. So we have 4 Box compounds: C3A, C3S, C2S, and C4AF. So we have to arrange these compounds in the ascending order with respect to the rate of strength gain. That is, which of them takes the least amount of time to gain its strength, and then we need to arrange the 4 compounds sequentially in terms of the rate of strength gain. Okay, so I think we can go ahead with the discussion now, with the answer in the discussion. So the correct response is option B. Okay, so here we can see the rate of strength gain of different compounds. Okay, so initially we have this particular graph where we have the curve which is represented by the diamond marker. So that corresponds to the compound C2S. Okay, C2S is responsible for a delayed attainment of strength. That is, its rate of strength gain is the least, you can say. Okay, so after that we have this particular curve, as you can see, which is having this circle marker, and that corresponds to C4AF. So after C2S, uh, the second uh, The second compound in terms of the rate of strength gain is C4AF. Okay, and then we have another curve after this, which is represented by this triangle marker, that is C3S, and ultimately we have the fourth curve, which is having the square markers, which is C3A. Okay, so essentially what we mean to say is that when these Box compounds, right, they undergo the process of hydration upon the chemical reaction between the cement and water. So these Box compounds are formed, and essentially C2S and C4AF, okay, their rate of strength gain is quite less as compared to the other compounds. Okay, so C3A and C3S, they are responsible for the high strength. Okay, so whenever we need to have or develop a high strength cement, we tend to increase the proportion of these two particular compounds. On the other hand, when we need delayed strength, delayed strength gain, then we increase the proportion of these two Box compounds, that is C2S and C4A. So this particular slide has been taken from the course lecture. Okay, so I think we can move on to the next question now, right? So which of the following statements are true about the process of delayed ettringite formation in concrete? Okay, please take 2 minutes and let me know what would be the right answer. So in today's session, we are going to discuss about 20 sample questions, which are going to help you to solve the assignment problems and develop an in-depth understanding of the concepts which were taught in this week's module. So it's going to be a mix of theoretical and numerical examples. Okay, so uh, I think I'm going to read out the options. Okay, so ettringite is an amorphous structure within concrete. Okay, and the second statement is low early heat, low early heat in concrete accelerates the process of ettringite formation. Okay, and the third statement is delayed ettringite formation leads to an increase in the concrete volume and subsequent cracking, which makes the reinforcing steel susceptible to corrosion. And the fourth statement is delayed ettringite formation can be prevented by curing the concrete at very high temperatures of 65 degrees Celsius and above. And the last statement is delayed ettringite formation can be mitigated by the use of pozzolanic materials in cement. So if you have understood or you have watched the week two lectures or the contents of week two, so you will know that out of these five statements, there are two statements which are correct. Okay, so the correct statements are option C and option E. Okay, and the remaining questions, so the remaining statements are incorrect. Okay, so let me go further and give you an explanation of this question. right? So I have attached a link in the presentation which you can refer in order to understand more about the delayed ettringite formation. Okay, so delayed ettringite formation is a deleterious chemical reaction in hardened concrete where ettringite, which is a sulfate containing mineral, forms after the concrete has hardened, leading to expansion, cracking, and durability issues. Okay, so ettringite is essentially a chemical reaction which is which occurs in the hardened concrete. Okay, so ettringite can be formed at an early stage also, but what is more detrimental to the durability of concrete is the formation of ettringite at a later stage when the concrete has hardened. Okay, and this tend to form a crystal-like structure. Okay, as you can see here, this picture is again taken from the lecture slide where the ettringite tends to have a crystal shape, right? And this crystal shape usually leads to an expansion of the concrete volume, leading to concrete. And once the concrete cracks, we know that moisture can easily seep into the volume of concrete, and there can be corrosion of the reinforcement, which leads to the durability issues, right? And so, as we can see, the early ettringite formation is not so harmful, but when it occurs at a later stage in the hardened concrete, that is detrimental to the durability of concrete, right? So we're going to be discussing little more in terms of the chemical reaction in the next slide. So let us look at the causes of delayed ettringite formation. So at high curing temperatures, that is above 65 degrees Celsius, so we can observe this phenomenon of delayed ettringite formation. And if the cement has a high sulfate content, again, it is uh, the concrete can have this DEF. Okay, it is prone to have developed DEF at a later stage. And if there is high moisture availability, so if the concrete is exposed to a high degree of moisture, again there is a probability of DEF happening. So again, remember that these factors alone are not responsible, but a combination of these factors can lead to the phenomenon of DEF. Okay, and then the fourth cause is uh, the cement composition, which is having a high C3A content. So as we can see, we can relate this concept to the first question, where C3A is having the highest rate of strength gain. So this leads to a lot of heat of hydration is more. So because of the heat of hydration, the temperature tends to rise and it leads to the DEF phenomenon at a later stage. And then if there is a lack of pozzolanic material, okay, there can be DEF. In fact, the use of pozzolana and other pozzolanic materials, it helps to bind the cement particles, and it actually prevents the formation of ettringite at a hardened state. Okay, so pozzolana is actually beneficial in preventing the DEF phenomenon, and ultimately a dense or a poorly ventilated concrete, right? That is susceptible to the DEF. Okay, so coming to the chemical reaction, so here we have the C3A, that is one of the Box compounds. It reacts with gypsum uh, and water, which leads to the formation of this ettringite. And this ettringite, it can further react with the C3A, which is present in cement, and form this monosulfo aluminate. Okay, so this particular reaction is reversible, okay, with the availability of water. So it tends to form this ettringite. So as we already discussed earlier, this is a image of ettringite in a microscope, a microscopic image of the ettringite. So ettringite with its crystalline structure, crystalline needle-like structure, it has a high volume, and because of the expansion of uh, the volume due to the DEF, there can be cracking within concrete. And as we know, cracking leads to porosity within concrete and other durability issues. So moving on, we can move on to the next question. So yeah, so this question is related to the stress strain curves of concrete cylinders under compression. Okay, kindly take 2 minutes and let me know what is the correct response. Okay, so I think I'll start reading out the options. So when we take a concrete cylinder and when we test them under compression, okay, so we get this stress strain curve, right? So the question is on the shape of the stress strain curve of concrete cylinders under compression. So as the grade of concrete increases, both the peak strain and the ultimate strain decrease. So that is option 1. Option 2 is as the grade of concrete increases, peak strain increases, but the ultimate strain decreases. Okay, that's option 2. Option 3 is as the grade of concrete increases, peak strain decreases, but the ultimate strain increases. Okay, and finally, option 4 is as the grade of concrete increases, both the peak strain as well as the ultimate strain increase. Okay, so out of these four options, the correct option is option B. Okay, so we can just take the help of this particular picture from the lecture slide, and we can answer this particular question. So so these different curves corresponds to concrete cylinders of different grade. So here we can see that uh, when we take concrete cylinders of higher uh, higher grade, okay, these are the hardened concrete cylinders, and then when we test them under compression, this is the kind of response that we can expect to obtain, right? So F prime C corresponds to the compressive strength of the concrete cylinders, right? So F prime C corresponds to the peak strength. So as we can see, as we increase the grade of concrete, right, the strength is increasing, f prime c is increasing, right? With the increase in the grade of concrete, epsilon peak is increasing. That is the strain corresponding to the peak stress, right? So we can see that by looking at the dotted lines, right? Let us say that this particular concrete is having an F prime C of 18 and this is having F prime C of 25 and so on. So we can see that the epsilon peak, that is the strain corresponding to the peak strength, that is increasing by increasing the grade of concrete, right? So with the increasing grade of concrete, epsilon peak increases. Okay. However, so epsilon ultimate or the ultimate strain, so this we can see that for this first curve, it is close to 0.004. Subsequently, we can see that it tends to follow a declining trend for higher grades of concrete. Okay. So to reiterate, when we increase the grade of concrete, right, epsilon peak is increasing, but epsilon ultimate is decreasing. Okay. So the strain corresponding to the peak strength is increasing, but the ultimate strain is decreasing, right? And because of this response, ductility is also reducing. So how do we define ductility? Ductility is nothing but the ratio of epsilon peak to, sorry, epsilon ultimate to epsilon peak. Okay. So as we can see here, if you take concretes of lower grade, so if you take epsilon peak, uh, sorry, epsilon ultimate to epsilon peak, it is close to value of 2, right? It is 0.004 to 0.002. But if you go to the highest grade of concrete which has been tested, so you can see that it is, you can consider by looking at the graph that epsilon ultimate is 0.0033 and epsilon peak is 0.003. So that is much lesser than the value of 2 that we obtained for the lowest grade of concrete. Okay. So in summary, we can say that by increasing the grade of concrete, epsilon peak increases, epsilon ultimate decreases, and the ductility also decreases. So we can say that statement B is correct. That is, as we increase the grade of concrete, the peak strain increases, but the ultimate strain decreases. In addition to that, ductility also decreases. Moving on, we have the fourth question. So we have a problem over here, numerical problem. So I would like to ask you to take 2 minutes and try to solve the example and let me know what is the right answer. Okay, so I think we can go ahead with the solution of this particular question, right? So first I'm going to tell you the answer, then we can look at the solution, right? So it is normal strength concrete. So for the normal strength concrete, we have the stress strain relation or the constitutive relation, which can be determined by the equation or the parabolic law given by Hocknestad. Okay, so this is again a slide from the weekly notes, weekly lecture. So let me take up, okay, I'm going to solve this numerically now. Let's take the pen. Okay, right. So I'm going to draw a small sketch over here. So we have this so let us consider that this is the cylinder and we are going to test it under compression, right? So for this particular cylinder under compression, we can use this constitutive relation. The stress strain relation is otherwise called as uh, constitutive the constitutive equation, which relates the stress to the strain, right? We have F prime C, sorry, yeah, Fc divided by F prime C is equal to 2 times epsilon C by epsilon prime C minus epsilon C by epsilon prime C whole square. Okay, so here let us look at what do each of these terms mean. So Fc is the stress in concrete. Okay, this is going to vary depending on epsilon c. Epsilon c is the strain in concrete. Okay, so here epsilon c is the independent variable and Fc is the dependent variable, and it depends on a lot of variables such as epsilon c, F prime c, and epsilon prime c. Okay, so we can see that as the epsilon c increases from 0 to epsilon peak, okay, it attains the highest load and then highest stress, and after that it reduces. Okay, so for this particular problem we have F prime C as 30 MPa and epsilon prime C as 0.002. We need to determine the Fc corresponding to epsilon C of 0.0015. Okay, quite straightforward. So let us start uh, writing the values given to us. F prime C is 30 MPa. Okay, then the strain corresponding to the peak stress, that is epsilon prime C, that is 0.002. Okay, and let us write down epsilon C also. Epsilon C, we need to determine Fc for epsilon C is equal to 0.0015. Okay, so for that, what will be the value of Fc? So this is the problem given to us. So to simplify this equation, let me simplify this epsilon C by epsilon prime C, that is 0.0015 divided by 0.002. Okay, so we have this becomes 0.75, right? So let us plug these values in the equation. Okay, so we have Fc is equal to, let me write down F prime C outside, that is 30 into 2 times 0.75 minus 0.75 square. Okay. Please, you can check in your calculator, calculate the value, and let me know what is the value of Fc. Meanwhile, I will also calculate the answer. So when I calculate, I get the value of Fc as 28.125. Okay, let me write down. So the value of Fc is 28.125 MPa. Okay, so using this Hognestad stress strain relation or the parabolic law, we can determine the stress strain relation of any concrete which is having a compressive strength of less than 40 MPa. Okay, and for concrete which is having a compressive strength of more than 40 MPa, we have the Thornfeld relation. Okay, so I'm going to so as we discussed, the correct answer is 28.125. That is option E. Okay, so I'm going to just reiterate the solution once again. So we have this concrete cylinder, okay, which is having F prime C, or the peak compressive strength of 30 MPa, and the corresponding strain is 0.002. So the peak strength is given by F prime C, and then the corresponding strain is given by epsilon prime C. We need to determine what is the stress in concrete corresponding to a strain of 0.0015. Okay, so when we use this parabolic equation or the Hognestad stress strain constitutive model, okay, when we plug these particular values in this equation, we obtain that corresponding to epsilon c of 0.0015, we got a value of Fc of 28.125 megapascal. Okay, so this is valid for all concretes which are having a strength of up to 40 MPa, and beyond 40 MPa we use the Hornfeld relation. Okay, so we'll proceed to the next question, right? So the next question is based on question 4 itself. So based on your understanding of week 2 lecture, I request you to take 2 minutes, try to solve the problem, and let me know what is the correct answer. Okay, so we are dealing with this question, which is a continuation of the previous question. Okay, so for those of us who joined now, I'm going to just write down the data, which is going to help them to calculate the correct answer. So we have F prime C is 30 MPa and epsilon prime C is 0.002. Okay, this is the data from the concrete cylinder test. So from that we need to determine the modulus of elasticity. Okay, so what is the equation for modulus of elasticity? Modulus of elasticity, that is EC, is given by 5000 square root of FCK. So to give you a hint, we are going to first, we have the cylinder strength. We're going to convert this to the cube strength. Then we're going to determine the characteristic strength FCK. From that, we're going to determine the modulus of elasticity of concrete. Okay. So take 2 minutes and let me know what would be the correct answer. Okay, so I think we can proceed with the solution for this particular question. So I'm going to give the answer first and then we're going to look at the solution, how it is being solved. So the correct answer is option C, that is 27041.6 MPa, right? So let us try to figure out how we, how we obtain this FCK from the cylinder strength. Okay. So, okay, there is no space over here. Let me try to work out here. Okay, so what we have is the cylinder strength. So if you want the cube strength, that is FCU, FCU is given by 1.25 into F prime C. Okay, so that is 1.25 into 30, sorry, 30, that is, excuse me, that is 37.5 MPa, right? 37.5 MPa. Okay, so from this, from FCU, that is the cube strength, how do we determine the FCK? Okay, so we need to take the help of IS 10262. Okay, so here we have the target mean strength FT, the target mean strength or FTM is equal to FCK plus 1.65 times the standard deviation. Okay, so let me try to open that document for you, right? So I hope that my screen is visible. Can anybody please confirm if you can? Okay, so as we can see, we have this target mean strength. So here it is given the notation as F prime CK, that is FCK plus 1.65 into S, right? So we can assume uh, we can consider this to come in this category between M30 to M60 and take a value of 5.0. Okay, excuse me. Yeah, so by considering the value of standard deviation as 5, we have FCK. FCK is equal to FTM or F prime CK, depends on the notation, minus 1.65 into S. That is 37.5 minus 1.65 into 5. So which gives us a value of 29.25. So this is the a calculation that you need to follow if you have the the cylinder strength. So you take the cylinder strength, that is 30 MPa in this case, multiply that by 1.25, you get the cube strength, and consider this cube strength as the mean target strength, that is F prime CQ or FPM. Then use this equation, divide the target strength by 1.65 times the standard deviation, and using the IS 10262 you get the standard deviation as 5. So from that you get the characteristic strength as 29.25. After that, to determine the Young's modulus of concrete, modulus of elasticity of concrete, you have EC is equal to 5000 into square root of FCK. You get the value of 27.27041.6 MPa, which is option C. Okay, so I think with that we can move on to the next question, right? So we need to cover another 15 questions in the next 1 hour, right? So this is pertaining to the high strength concrete. Okay, so uh, for a concrete which is having a peak cylinder strength, that is F prime C of 60 MPa, what is the stress Fc corresponding to a strain of 0.001? Okay, so yeah, so since this is a high strength concrete, we need to use the relation given by Thornfield. So we're going to use the Thornfield equation and not the Ogdenstad equation, and then we are going to determine the value of Fc. Okay, please take 2 minutes and we can start with the solution. Okay, so I think I'm going to give the solution and I'm going to start solving the problem simultaneously so that we can yeah, save time. So for this, the correct answer was option D. So as I said, the stress in concrete or FC is determined using the Thornfield stress strain relation for high grade concrete, right? So we have, yeah, this is the equation. So ultimately, we have the constitutive relation. Let me write down the constitutive relation over here. take a pen here. I'll take maybe a different color. Yeah. So we have FC by F prime C is equal to N into epsilon C by epsilon prime C divided by N minus 1 plus epsilon C by epsilon prime C raised to the power N into K. Okay. So here we can see that in comparison to the Hognestad relation, we have some new terms such as N and K. Okay. So we're going to find out what each of them represent, right? So here N is given by, yeah, N is given by 0.8. So as we can see in this equation, N is 0.8 plus. So there is a small correction actually, even in the lecture also, sir has corrected this formula, but in the PDF somehow it has remained like that. So it is not FCK, instead it is FCU by 21.25. Okay, so let us go ahead and calculate this, right? Okay, we have N is equal to 0.8 plus. So how do we determine the cube strength? That is 1.25 times the cylinder strength. That is 60 into 1.25. That will give us the value of FCU divided by 21.25. So based on my calculation, I'm getting a value of N as how much? 4.33. Okay. I'm getting the value of N as 4.33. Moving on, we need to determine the value of K, right? So we have K is equal to 0.67 plus FCK by 77.5. So here the value of FCK is correct. Okay, so from the cube strength, we need to determine the value of FCK. So as I was already telling you, we have the relation between, let me take another color for better clarity. We have the target mean strength is F prime CK is equal to FCK plus 1.65 times S. S is the standard deviation. Now we have the value of F prime CK as 60 into 1.25, that is 75 basically, right? 75 is equal to FCK plus 1.65 into, for the standard deviation, let us look at the IS code once again, right? So we can take the value of so we can consider a value of 6 actually. I think 6 holds good. Standard deviation of 6 we can take, because the value of 6 is applicable for grades between 65 to 80. Okay. Yeah, so we can take the value of 6 and we can proceed with our calculations, right? So for this particular value, we get the value of FCK as how much? I'm also calculating side by side. 75 minus 1.65 into 6. So that gives us a value of 65.1 MPa. Okay, FCK is 65.1 MPa. So if we go back to the table for a value of 65, yeah, for a value of 65, the standard deviation of 6 holds good. Okay, so now we have the value of n. Let us find out the value of k, right? K is equal to 0.67 plus 65.1 divided by 77.5. So the value of k is 0.67 plus 65.1 divided by 77.5. So I'm getting a value of 1.51. Okay. So the value of k is 1.51. So we need to plug these values n and k in this equation. Again, to simplify, I'm going to so before that we need to find out the value of epsilon prime c as well. Okay. Yeah, so we need to find out the value of epsilon prime c. So let me take another color. Yes, epsilon prime c. Uh, the numerical for this particular problem is a bit more involved, but for the remaining questions, I guess it is not so difficult for this particular module. So epsilon prime c is 0.8 FCU. Again, I request you to make this correction, right? So this correction has been made in the notes as well, but it is not reflected in the PDF. This is not FCK, but this is FCU, 0.8 FCU by EC. Okay, EC into n divided by n minus 1. Okay, let us start substituting. That is 0.8. What is FCU? FCU is 75 and EC is okay. So EC is 5000 root FCK, 5000 root 65 point, sorry, 65.1 into what is the value of n? N is 4.33 by n minus 1, that is 3.33. So let us see what is the value of epsilon prime c that we're going to get. Okay, I'm also calculating along with you. 6000 square root of, I'm doing the denominator first, 0.8 into 75. Okay, I'm getting a value of 0.00193. Okay, this is the value of epsilon prime c that I am getting. Okay, let us substitute here. Huh. So before proceeding further, we'll find out the value of epsilon c by epsilon prime c, that is 0.001, right, by 0.00193. I'm getting a value of 0.517. Okay, 0.517. Okay. Okay, now for the final step. Yeah, So we have all the values sorted out. Fc is equal to, what is F prime C? F prime C was 60, if I'm not mistaken. Okay. Okay, so F prime C was 60 into, let us take, n is, yeah, as we already saw, 4.33 into epsilon c by epsilon prime c is 0.517, 0.517 divided by n minus 1 is 3.33 plus 0.517 raised to the power, to close the bracket here. What is n? N is 4.33 into k. K is 1.51. Okay, apologies for this messy calculation, right? So I hope you can still follow. Anyway, my text, my speech is there. You can always follow this transcript. So let us, calculate and find out what is the value of FC for this particular value, right? 4.33 into 1. Okay, so when I calculate, I'm getting the final answer as 38.89. Okay, I'm getting a value of FC as 38.89 MPa. Okay, so you can always, perform the calculation yourself and verify what is the answer that you're getting. So in these cases, there can be some small mistakes, or there can be small approximation while calculating these values. We have calculated a whole lot of terms such as n, k, epsilon, prime c, and so on. So in that case, I suggest that you pick whichever is closest to the answer. So when I was calculating, I got the value between 38 and 40. So yeah, I got the exact value, in fact, of 38.89. So you can always pick whichever is closest to your response. Okay. So uh, let us move on to the next question, right? So the correct answer for this particular question is option D, that is 38.89 MPa. So for the concrete that is mentioned in question 6, what is the modulus of elasticity? So modulus of elasticity we have already calculated, but we have not written explicitly. So I'm not going to take much time. I'm going to just uh, go ahead with the answer, right? So, okay, so we have used this particular equation from the previous slide. So from the previous slide, we have modulus of elasticity is WC. WC is the density of concrete in kg per meter cube, power 1.5 into 0.00.0385 into square root of FCU. Again, I request you to make the correction, right? So let us start plugging the values and see what is the value we get here. Okay, so we have EC is, okay, EC, that is modulus of elasticity of concrete, taking WC as 2400, kg per meter cube raised to the power 1.5 into 0.0385 into square root of FCU. FCU is 1.25 into 60, that is 75. So when you solve this, you get the value of EC as 39202 MPa. Okay, so remember, for plain concrete, we take the density as 2400 kg per meter cube if there is no data given, and for reinforced concrete we take a value of 2500 kg per meter cube. Okay, so this is how we are going to calculate the modulus of elasticity of concrete. Moving on, so this is based on the mean target strength of IS 10262 that I've already introduced this code to you, IS 10262. So if you have followed the discussion so far and the discussions from the weekly lecture, I request you to attempt this question and let me know what is the correct answer. Okay, so going to give you a hint again. So the mean target strength, or F prime CK, as per this code is FCK plus 1.65 times standard deviation, right? So we can take FCK as 30, and what would be the standard deviation? Let us look at the code once again for M30 mixed concrete. So for M30 mixed concrete, we can take the standard deviation as 5.0. So what do we get? We get mean target strength of 38.25 MPa. Okay, 38.25 MPa, which is option B. Okay, so I think we can move on to the next question now. Yeah, the characteristic strength is defined as the strength of material below which not more than 5% of the test results are expected to fall. Do we have an explanation? Let me see. Okay, no, we don't. So hence the mean target strength is determined from the code IS 10262 2009. I think it has been updated to 2016. In the year 2016, yeah, oh no, in 2018 it has been updated, 2019. So we can follow this code and obtain the mean target strength. Okay, so just to give a very brief theoretical background of this target strength, sir has already covered it in the class, but I would like to share a few insights, right? So if you plot uh, you know the strength over here, okay, if this is the strength of concrete, let us say FCU, okay, it tends to follow a bell curve, right? It tends to follow a bell curve with this value of this is the mean target strength F prime CK, and this is the value of this is the value of FCK, and we need to ensure that in order to for the concrete to qualify as M30, right? 95% of the samples tested have to fall in this region. Okay, only 5% may be allowed to fall less than 30 MPa. So if we have casted and tested 100 cubes, right, 95 95 of these cubes have to be more than this value of 30 MPa, so that the concrete can qualify as M30 concrete. Okay, so that is the theoretical or the conceptual definition of the M30 concrete. So we will move on to the next question now, right? So here is uh, the clause 4.2 of IS 1026 to 2019, and we can see that we have two equations. We can use both these equations, they're equally good. So I prefer to use the first one, that is f prime c is equal to, I'll take the laser, f prime ck is equal to fck plus 1.65 into s, and the value of s can be obtained from table 2 of this IS code. Move on, we'll move on to the next question now. So question 9, what is the design compressive strength of M40 concrete as per the provision of IS 456 2000? Okay, so we looked at the characteristic strength, then we have the mean target strength. Now what is the design compressive strength? Okay, take 2 minutes and let me know what is the right answer. Okay, it is a simple straightforward question. So let us look at the answer now, because we need to cover another 11 questions before 9 o'clock in another 40 minutes, right? So the correct answer is 7.87. Let us look at the explanation. Okay, so as we can see here, this curve has been adopted from IS 456. Okay, so figure 21 and 22. Now let us look at the class lecture, the class lecture slides for a clearer understanding. So as we already mentioned, I'll take the so first we have the concrete cylinder strength, right? So we have seen that in order to obtain the cube strength, we take the cylinder strength and then we multiply it by 1.25, or else if we want to obtain the cylinder strength from the cube strength, we multiply it by factor of zero 0.8, right? We multiply the cube strength by a factor of 0.8. Okay, Further, in order to consider the side effect, we are going to multiply this by a factor of 0.85. Okay, so if you are wondering uh, how we are going to obtain this 0.67, okay, so this is the hint. So from the value of FCK to the real life structures, so first we are going to multiply the cylinder strength by 0.8, sorry, the cube strength by 0.8. Then we are going to multiply it by a factor of 0.85. So 0.8 into 0.85, sorry, 0.8 into 0.85 gives us the factor of 0.67 FCK. Okay, that is how we are going to get accounting for the cube strength to the cylinder strength, and then 0.85 to accommodate the size of it. So we are going to take this value of 0.67, then we are going to divide that by a partial safety factor of 1.5. Okay, this is how we are going to get the design curve of 0.447 FCK. Okay, so let us go back and plug this value. Okay, so 0.447 into 40 gives us the design compressive strength, that is 0.447 into 40 gives us a value of 17.88 or 17.87. Sorry. Okay. Okay. Excuse me. 17.87 MPa, right? 17.87 MPa. Okay. So with that, I think we can proceed to the next question now. Yeah, so these are the corresponding graphs from the IS 456. So next question is for M40 concrete prism, which is having a dimensions of 100 mm by 100 mm. It's a square cross section. It is subjected to a 4-point bending test. If the maximum bending moment is 1 kilonewton meter, what is the corresponding flexural stress that is developed? Compare it with the modulus of rupture. Okay, kindly take 1 or 2 minutes and let me know what is the correct answer. I'm going to solve it side by side. So we have a square cross section of concrete having 100 by 100. So we have m by I is equal to sigma by y. Or you can also write it as sigma is equal to m divided by I by y or m by z. So section modulus is nothing but m by bd square by 6. Okay, let us start plugging the values in the equation. Sigma is, I'll convert uh, this moment from kilonewton meter to Newton millimeter. That is 1 into 10 to the power 6 Newton millimeter divided by BT square by 6. So both B and D are 100 millimeter each. So I'm going to write it as 100 cube divided by 6, which gives us a value of sigma of how much? I'm getting a value of 6 MPa, right? Got a value of 6 MPa. Now, how do we determine the modulus of rupture? What is the equation? Okay. Okay. Let us see what is the equation for modulus of rupture. So we got the flexural stress as 6 MPa from this particular equation, that is 6m by bd square, or m by bd square divided by 6, right? And modulus of rupture is 0.7 root FCK. Okay, let me solve it over here. That is modulus of rupture FCR is 0.7 square root of FCK, right? So we have taken M40 concrete, that is 0.7 square root of 40, which gives us a value of 0.7 to 40, 4.43 megapascal. 4.43 megapascal, right? So the maximum flexural stress is 6 MPa and the modulus of rupture is 4.43 MPa. The correct answer is option D, and as we have seen in the class lecture also, the modulus of rupture is determined using this particular equation, which is taken from clause 6.2.2 of IS 456. Okay, moving on. Yeah, so we are going to transition from the numerical problems to the conceptual ones. Identify the incorrect statement with respect to the concept of tension stiffening in reinforced concrete. Okay, let me just check if how many numerical problems we have from this point onwards. Okay, yeah, we have one problem. Okay, okay, right. I think we have one more numerical problem. That's it. Okay, so we have the problem, we have the question on tension stiffening, right? Take 1 or 2 minutes and let me know what is the right answer. So we have the concept of tension stiffening in reinforced concrete. We need to identify the incorrect statement among the statements that are given. So I'm going to read out each statement one by one. It is defined as the effect of concrete acting in tension between the cracks in steel reinforcement. Okay. The second statement is okay. So the second statement is at the location of cracks, loads are resisted entirely, sorry, by the steel reinforcement. However, in between the cracks, part of loads are also resisted by concrete. The third statement is it leads to an increase in the stress and strain in the reinforcement. And the fourth statement is adequate bond between steel reinforcement and concrete leads to a stiffer load deformation response under tension. So out of these four statements, which one is the incorrect statement? So the incorrect statement is option C. Okay, option C is wrong. Okay, so tension stiffening is the effect of concrete acting in tension between the cracks. So here, as we can see, wherever there is crack in the concrete, in the reinforced concrete, so there the load is entirely resisted by the rebars. However, in between the cracks in the concrete, a part of the tensile stresses are resisted by concrete as well. Okay, in addition to the rebar, it is resisted by the concrete as well. Okay, this phenomenon is called as tension stiffening, and all the statements are correct except the statement C. And wherever there is this tension stiffening, because the concrete resists a part of tensile stresses and strains, the stress and the strain in the rebar is slightly reduced. Okay, so it leads to a reduction in the reinforcement stresses and strain. Okay, between the cracked region. Okay, so here in option C, it has to be, it leads to a decrease in the stresses and strain in the reinforcement. Okay, and it leads to a stiffer stress strain response. Okay, so option C is the incorrect statement, and option A, B, and D are correct. Okay, so moving on. So here the question is based on the shrinkage and creep in concrete. Okay, so the question is to chronologically arrange the following components of shrinkage and creep within concrete during the service life of a structure. Okay, please take 2 minutes and let me know what is the correct response. Okay, so the correct sequence of the formation of shrinkage and creep is option B. Okay, so let us look at the diagram over here, which explains the various stages of formation of shrinkage and creep within the concrete. Okay, so here autogeneous shrinkage, that is something which is related to the hydration of cement. So as the hydration occurs, there is shrinkage in concrete. So we have the autogeneous shrinkage first, and then we have the drying shrinkage. So drying shrinkage refers to uh, the shrinkage which is occurring due to the evaporation of the water. Okay, so as we can see, first we have the autogenous shrinkage, which starts with the which starts with the hydration of cement compounds. Then we have the shrinkage, the drying shrinkage. After that, once the concrete is set, that is ideally after 28 days, so there is some initial loading. there is some further construction activity which can take place. So we have the load induced strain, and then after a certain time we have the creep strain, sorry, the creep strain. And the creep strain is uh, usually uh, the creep strain is what is known as the deformation that is uh, age related. After a certain time, the strain that is induced is called as a creep strain. Okay, so the correct sequence is autogenous shrinkage due to the hydration of cement, drying shrinkage due to the evaporation of concrete, evaporation of water in concrete. Then we have the load induced strain. Then ultimately we have the creep strain, and creep is nothing but the deformations under the sustained loading conditions. Moving on, identify the correct statement with respect to the concepts of creep and shrinkage. Okay, please take 2 minutes and let me know what is the correct response. So there are multiple correct statements in this state. In this, there could be multiple correct statements in this question. Okay, so think for a while and let me know what is the correct response. Okay, so out of the four statements, the correct statement is option A. Okay, so the first statement is nothing but the definition of creep. So creep is defined as the long-term deformation caused by the application of loads over a long period of time. Okay, the second statement is creep deformations cannot be reversed upon the removal of loads, but it is wrong. When you remove the loads, there can be reversal of the creep deformations as well. Okay. So I think there is a statement, yeah, there is a figure which can represent that. So here, with the removal of load, there can be recovery of creep as well. So the statement 2 is incorrect. And the third statement, shrinkage is referred to an increase in the volume of concrete. No, shrinkage is referred to as the decrease in the volume of concrete due to the loss of moisture. Okay. The fourth statement is the factors responsible for creep and shrinkage differ largely from each other. Again, it is incorrect statement. The factors which are responsible for creep and shrinkage are more or less the same. I'm not going to say that they're exactly the same, but they are more or less the same. Okay, so out of these four statements, option A or the statement A is the correct statement, and the remaining statements are incorrect. Okay, so this is the representation of the variation of creep strain along with time. Okay, and this is with respect to the shrinkage, right? So moving on, moving to the next question. So determine the effective elastic modulus of M30 concrete after a period of 28 days and 1 year to determine the deflection due to 3. Okay. So I'm going to give you a hint, so that we can start solving the problem together, right? So whenever we have the uh, effective elastic modulus, we can determine using this equation, that is effective elastic modulus is given by effective modulus is given by E divided by 1 plus theta. Okay. So E or EC is the modulus of elasticity of concrete, and theta is the coefficient that varies depending on uh, the duration. Okay, the duration where we are going to calculate the deflection due to creep. Okay, now let us look at the solution and then the corresponding equations. Yeah, so we can basically start solving from here, right? So first we have EC. Okay, EC is 5000 square root of FCK, right? So FCK, as we know, is 30 MPa, 5000 square root of 30. So which gives us a value of how much? 27.386 GPa, right? 27.386 GPa. Okay, it can be expressed as 27,386 MPa also, but I am expressing it as GPa for convenience, right? And in order to determine the effective modulus, that is ECE, we can use the equation of EC divided by 1 plus. So we need to determine for 28 days and 1 year. So 1 plus 1.6 for 28 days, and for 1 year we have ECE is equal to EC divided by 1 plus 1.1. So by solving the equation we get 27.386 divided by 2.6 and 27.386 divided by 2.2. We get the corresponding value as 10.53 and 13.04. 10.53 GPa and 13.04 GPA. Okay, so option A is the correct answer. So moving on, we'll move on to the next question, right? Yeah, so this is these values are taken from clause 6.2.5.1 from IS 456. Moving on, identify the correct statement with respect to the shrinkage in concrete. So out of these 4 statements, we have only one statement which is correct and the remaining are incorrect. Shrinkage depends on the stress conditions in concrete due to the effect of external loads. Shrinkage is irreversible and does not depend on the moisture content available in the environment. Concrete structural elements with low surface area to volume ratio experience high level of shrinkage. Lastly, the type of aggregates and admixture used in the type of aggregates and admixture used in the concrete influence the shrinkage in concrete. Okay. So out of these statements, which one is the correct statement? So option D is the correct statement. Okay. So let us look at the reasons. Okay. So the shrinkage is independent of the external loading conditions, as we can see, from the lecture slides over here. It is independent of the stress conditions due to external loads. Shrinkage is indeed reversible and it depends on the moisture content. Okay. So shrinkage, as we can see, it can be reversed because of the moisture content, right? It is reversible to a great extent depending on the moisture conditions, right? And concrete elements with low surface area to volume experience high level of shrinkage. No, it is actually the opposite. If you are having a low surface area, then the level of shrinkage is also reduced. And finally, the type of aggregates and admixture are responsible for the shrinkage within concrete. So this particular statement is correct. Option D is correct, whereas the option A statements A, B, and C are incorrect. Okay. So we'll move on to the next question, right? Which of the following statements is incorrect about the carbonation shrinkage? Okay. Please take 2 minutes and let me know what is the correct answer. Okay, so let us look at the answer now. So out of these statements, option B is incorrect. Okay. Carbon shrinkage is a phenomena which occurs when the calcium hydroxide which is present in fresh concrete reacts with the carbon dioxide, leading to the formation of calcium carbonate and water, which leads to the shrinkage in concrete. Okay, so this statement is correct. And the formation of calcium carbonate reduces the pH of concrete. Okay, so if we consider concrete, an alkaline medium is generally preferred because it leads to protective oxide film around the steel rebars. But due to the formation of calcium carbonate, there can be a reduction in the pH value, because of which the protective oxide film can dissipate away. And because of this dissipation, what happens is that there can be uh, the corrosion of rebar because of the destruction of the protective oxide film. Okay. And statement D is correct because carbonation shrinkage leads to volume reduction as well as the corrosion of steel rebars from the lowering of pH. Okay. So yeah, please make this correction. Actually, here it has to be hardened concrete and not fresh concrete. So if you consider that, option B is incorrect, and here uh, it has to be hardened concrete. Okay. So as I said, it is the reaction between the calcium hydroxide, right, along with carbon dioxide, which leads to a reduction in the pH value. And because of the reduction, Okay, the protective oxide film uh, surrounding the rebar that gets dissipated or destroyed, and the rebar becomes susceptible to the corrosion. Okay, so in this question, option B is the incorrect statement. Remaining statements are correct. And again, please make this correction from fresh concrete to the hardened concrete. Moving on, the next question is, what are the yield strains of mild steel, that is Fe250, and high strength yield, uh, high strength yield, high yield deformed bars? Okay, high yield strength deformed bars corresponding to a stress of 0.87 Fy. Okay, kindly let me know what is the response, what is the correct answer. Okay, because of the shortage of time, we only have 10 minutes, so I'm going to rush through the remaining problems quickly. Okay, for the mild steel, the correct answer is option B. So for the mild steel, you're going to just use this equation. That is, we know that the strain is given by stress upon Young's modulus, that is 0.87 divided by ES, that is 0.87 into 250 divided by 2 into 10 to the power 5, gives us a value of 0.0011. And for Fe415, we are going to determine by 0.2% offset method, that is 0.002 plus 0.87 Fy divided by Es, that is 0.87 into 415 divided by 2 into 10 to the power 5, which gives us a value of 0.0038. Okay, so option B is the right answer, and the strain corresponding to a value of 0.87 Fy for mild steel rebars and HYST rebars are 0.0011 and 0.0038. Moving on, yeah, this is the representation over here. Okay, here we're going to divide it by ES straight away, and here we're going to use the 0.2% offset method. So the next question is, as per the IS code, what is the minimum elongation of steel bars required for seismic zones 3, 4, and 5? So this is a conceptual question uh, based on IS 13920, right, which is for the earthquake resistant design of reinforced concrete structures. And as per this code, the minimum elongation of steel bars that is required is option D, that is 14.5%. Okay, so please note that yeah, it should be option D, not C. There is a mistake, right? As per IS 13920 which deals with the ductile detailing and design of reinforced concrete structures subjected to seismic forces for steel rebars in used in the buildings which are located in seismic zones 3, 4, and 5. These rebars should have a minimum elongation of 14.5%. Okay, option D is the right answer. And here is the clause as per the clause 5.3 and 5.3.1 of IS 13920 the rebars should have a minimum elongation of 14.5%. Moving on, we have two more questions for today's live interaction session. So, arrange the following types of rebars in terms of the decreasing value of the modulus of elasticity. Okay, so we have 5 rebars: pyramid fiber reinforced polymer, carbon FRP, glass FRP, reinforcing steel, and finally the restressing steel. Okay, so we need to arrange these rebars in terms of the decreasing value of the modulus of elasticity. So we need to put the rebars with the highest value of modulus of elasticity and place the other rebars in a decreasing order. Right? So I think we can go ahead with the solution now. So we have the steel which is used in the pre-stressing the pre-stressed concrete structures and the reinforced concrete structures. It is the same. Okay. So the correct answer is option D. The modulus of elasticity of the pre-stressing steel and the reinforcing steel both are the same. That is 200 GPa, which is followed by the carbon FRP rebars, which is followed by the aramid FRP bars, followed by the glass FRP bars. Okay. So here we can see the representation. The the black line over here corresponds to the pre-stressed steel as well as the reinforcing steel. Then the CFRP rebars, which is represented by the blue line. Then we have the AFRP, aramid FRP bars given by the green line, and then the GFRP bars given by the yellow line. So CFRP, AFRP, and the GRP, they have the decreasing values of the modulus of elasticity. Okay, and just to give a representative value, the modulus of elasticity of GFRP bars is about 20 to 25% of the modulus of elasticity of the steel rebars. Okay, which is, as you can see, it varies between a value of 40 to 60 GPa. So moving to the last question for today's session, identify the incorrect statement with respect to the cold twisted bars. Okay, take a few seconds and let me know what is the right answer. So we have the cold twisted bars or the deformed bars. Okay, I'm going to read out the statement and wind up today's session. They are processed through the cold twisting process. Okay, that is the first statement. Plain round steel bars are twisted in a cold state of around minus 200 degrees Celsius using specialized equipment. Second statement. Third statement is yield stress of cold twisted bars is about 50% higher than the mild steel bars. Next statement is twisting process improves the overall bond strength with concrete. Fifth statement is twisting may induce surface defects due to subjecting the rebar to torsional stresses. So out of these five statements, we can say that option B is incorrect. Okay, remaining remaining statements are correct. Okay, because let me go statement by statement. Yes, the CTB bars are processed through a cold twisting process, but they're not subjected to sub-zero temperatures. Usually they're twisted at room temperature or near room temperatures only, right? And the yield stress of uh, cold twisted bars is about 50% higher than the mild steel rebars. That is correct. And the twisting, it creates ribs in the rebars, which improves the overall bond strength with respect to concrete. And finally, the twisting can induce surface defects because of subjecting the rebar to the torsional stresses. Okay, so option B is the only incorrect statement, whereas the other four statements are correct. And yeah, so this is the slide adopted from the class lecture. And with this, I think we can say that today's session has come to an end. And I thank all the participants who have joined today's session. And I request the remaining participants to get back, to watch the YouTube recording, which I'm going to upload tomorrow, and get back to me if there is any doubts. Okay. And yeah, thank you, and meet you all next week.